Every challenge question, part 40. This is Corporeal 1, chapter 7, which looks like it's the linear transformations chapter. Good. Now, you could do this by considering T to be a matrix of the form 2 minus 3, 1, 1, I guess. 2 minus 3 this way and then 1, 1 this way. Otherwise, you can literally just say, well, if you shove kx, ky into it, this becomes 2 times kx minus 3 times ky into this. You can factorize out a k from all of that. And this is just k lots of what t of xy is based on this definition here. So I just did that. And likewise here, I just added up these two things here and then said t of this is just 2 times this bit here, which is all of that, minus 3 lots of this one here, which is just acting as this one here. So that's that. And then there, and then you can break this, you can expand this out and then put all the x ones first and y ones first. And then you can say this vector here is just these two things and these two things plus those two things and those two things. And this is just t of x1, y1, and this is just t of x2, y2. And therefore, we get from here to here. So yeah, that was pretty straightforward. Proving this is kind of interesting, so that's nice. We're going to take a coordinate xy somewhere in the coordinate plane, which has maybe a distance of r away from the center, the origin. And if we rotate that around, if we say this angle here is alpha, we can actually say first that the x-coordinate is defined to be r cos of alpha. That's just how cos of alpha works, but if you want to, you can draw a triangle here and do some SOHCAHTOA. But anyway, y is also r sine of alpha. And now if you rotate this point around somewhere over here, maybe angle beta, who really cares, the magnitude is not going to change because it's a rotation. And we're going to get to some new point x dash y dash. But we can describe x dash y dash in the same way as these two, in the sense that if we think about a triangle that kind of exists here, the angle is alpha plus beta, it's right angled. And so y dashed is r sine of alpha plus beta, and x dash is r cos alpha plus beta. But of course, now we can use the compound angle identities that we learn in year 13 regular maths to say that this is this, and this is this. That's in the formula book, so I've just used that. But of course, r cos alpha and r sine alpha are x and y, and likewise down here, that's also x and y, so we get to this here. And so therefore, x dash y dashed is this. But actually, you can form that into a matrix, and the matrix is just this, right? X dash is x cos beta minus y sine beta, that's right there. And y dashed is sine beta x, which is here, plus cos beta y, which is here. And so this is the correct matrix to rotate by angle beta, and therefore this to rotate theta, I guess, anti-clockwise about the origin. And so that's done. Quite a nice little question. Anyway, this is a weird question. The determinant is 7 times 0 minus 0 times 0, which is 0. And even weirder, if you just take a point xy and multiply it by this matrix, you get 7x plus 0y as your top term into 0 plus 0. And this is on the x-axis because there is no, the magnitude of the y-coordinate is 0. So it's on the x-axis. That's literally that entire challenge question. I'm very confused about it. Given p is this, show p squared is that. So okay, just do p times p. This is going to be cos squared minus sine squared as your first bit, and then minus sine cos as your second bit, which is minus 2 sine cos there. And then for the other bits, of course, it's going to be sine cos plus sine cos, which is 2 sine cos, and then minus sine squared plus cos squared. Now, again, using some identities that I couldn't be bothered to write down, cos squared minus sine squared is cos 2 theta, and 2 cos theta sine theta is sine 2 theta, which means this is minus 2 sine theta. Sorry, this is minus sine 2 theta, and this here, you just swap them over, is again just cos 2 theta, and you end up here, which is what they want you to get. Interpret this geometrically, I just said it means that if you rotate, this is a rotation matrix, right? So just doing one of these rotations followed by another of the same rotation is the same as just rotating it twice as far. Something like that, I don't know, something like that will be okay. Find a 3x3 matrix representing reflection x equals 0 followed by y in the plane x equals 0 followed by y equals 0. Now, if you reflect in the plane x equals 0, that means your x-coordinate goes from a positive to a negative or vice versa, but the same altitude. So x turns into negative x. And likewise, reflection in the plane y equals 0, y turns to negative y. And the z-coordinate doesn't change at all on either of those things. So we're looking for a matrix that's going to send, when you multiply by x, y, z, is going to get it to minus x minus y, z. And it's fairly easy to just come up with this matrix for doing that. This is clearly going to work. And so this is the matrix. You could also do that, and I'll do it differently in the second part, by just considering each transformation as its own thing and just using the standard results. So for example, if you're taking the point x, y, z here, the standard result for rotating 45 degrees around the x-axis is this here. It's in the book. So I've just put in cos of 45 and sine of 45 into these things, which makes this. and then followed by a reflection in the x-plane. Again, this is in the book, it's just here. This is a reflection in the x-plane, very similar to what I said before, it's just swapping the x-axis and nothing else, or the x-coordinate. And now we just expand this out, and it looks like it's going to be a mess, but it actually turns out right? Because the zeros mean most of the things are just zero. In fact, nothing changes except this turns into a -1, and that'll be matrix there. But otherwise, just expand it out. Again, almost everything turns into zero. Find the 3x3 matrix that does a reflection in the y equals 0. So that's first. So that's just going to be this one with a -1 here. Rotation 90 degrees in the x-axis, or about the x-axis, is this here with these 90s. Now cos of 90 is -1, and sine of 90 is, cos of 90 is 0, and sine of 90 is 1. So it's going to be 0, 0, -1, 1. So that's there. And then followed by reflection in plane z equals 0 is this one, but with the minus bit there instead. And now we're just going to multiply out left to right. So let's multiply these two first. Again, the zeros make most of these things 0. You end up with this here. All that really changes is that this one here turns into a -1, because that comes from doing this times this. So the -1 times 1 here is that. And yeah, then we can do obviously these two times together. Again, not a lot changes there. You just end up with this here as your answer. If you do that multiplying out, you can do it more carefully if you want. But anyway, therefore, this is the matrix that represents all three of these things. Last one here. So show that this transformation maps any point onto x, y equals x. So okay, well, any point is just xy. If you times these out, you just get yy. And this is on the line y equals x because the x coordinate, which is y, is equal to the y coordinate, which is y. So it's on the line y equals x because the two coordinates are equal to each other. Next, we're trying to get it onto the line y equals mx. If you use this matrix here, multiply out, you just get y and then my. And this is fine because the y coordinate, which is my, is equal to m times the x coordinate, which is y. So replacing this with my and this with y, you get my equals my, and that's great. So it's satisfied. So this will be the matrix that does it. Explain why this is not a linear transformation, this thing here. Linear transformations are defined to be a transformation where 0, 0 goes to 0, 0. However, this line doesn't necessarily go through 0, 0. It only does it if c is 0. So unless c is 0, there's no way for you to transform 0, 0 and put it on 0, 0 because you have to put it on this line, and this line doesn't necessarily even go through 0, 0. So you can't map there unless c is 0. So this is why it says in general, right? If c is 0, then great, it's linear because you could map 0, 0 to 0, 0. But if c isn't 0, this doesn't go through 0, 0, therefore you can't map the origin to the origin because it's not on there. So therefore it wouldn't be linear. And that's basically what I have to say.